pendulum. All right? A pendulum means you take this, tie it onto a string, all right, and you set it in motion like that. Take anything, put it on a string, and it's moving back and forth. Now, let's say the factor that we're trying to figure out is how much time it takes to make one complete cycle, like this and back, or from here up and down. One complete cycle, or from here and up. Okay? How much time does it take to complete a cycle? What would you say it depends on? What are the factors that such a thing should depend on? How fast it's going. Okay. Now, let's say I just let it go from here. What is how fast? What is the speed with which it's going to go? Is it going to depend on what? Okay, so we have a few suggestions. We have the angle, the weight, and gravity. But gravity and the weight are related. Basically, the mass and the acceleration of gravity. Okay. What else? Anything else?
You push it or not?
Okay, let's say I'm not pushing it. I'm just letting it go. So, anything else? Now, let's say I took.
The resistance of the
What
string.
was that? What about the string? Okay. Okay. Let's assume that I have, right? But if it's just swinging, then it won't much matter because it's not going to buckle. If I push it, like if you push on a swing, it buckles. I'm not pushing on it. I'm just letting it go by itself. So any string will actually be good.
Also, if on top, it's like
Friction between what and what? Well, let's say just I'm holding the string. So there would be air friction, of course. Okay, air resistance. But let's say I'm neglecting the air resistance. Okay, why would the length of the string be important?
The distance traveled.
Why do you say the length is important?
Well, the longer it is, the longer the arc will be.
Okay, well, the longer it is, the longer the arc will be. So in other words, it's covering a larger distance.
Yeah.
Okay, does that matter or not? What would you say?
Yeah,
Well,
travel distance.
okay, if you think of an extreme example, let's say you have a string that's a mile long, all right, and you hold it up over here, it's going through a really big distance, right? If you have a string like this, it's going through a pendulum motion like this, and this is a mile, then this is about a mile. It's got to cover about a mile distance. If you take a smaller string, okay, and you make it go up like this, like that, it's obviously not going to take that long. Okay, if you take a string and hold it here like this, it's going to cover in a second, let's say. If the string is a mile long, it has to cover about a mile of distance to get back up again. All right? Because it's following with gravity. So if I let it go and it's a mile long, it's going to fall with the same acceleration, g. It doesn't matter if it's a mile long or 2 inches long, it's going to fall with the same acceleration, g. So certainly the amount of time is going to depend on the length of the string, on the angle theta that you held it at. Obviously it takes more time if it's up here than it's up here. And then on the mass and the gravity. Now it turns out, why would I say that there's a reason that it might not depend on the mass? Why might it not depend on the mass? Because the only reason that you might think that it depends on the mass is how fast it's going to go. But how fast it's going to go is determined only by gravity, and as we know, everything falls with the same acceleration irrespective of the mass. So it turns out that it does depend on the acceleration due to gravity, but not on the mass. Happens.
Gravity's constant.
Right, but in different planets or further away from the planet or something like that. In other words, where are we changing g? Because it depends on that. It's true that all our experiments will take place basically with the same g, but it does depend on it. Now, for small angles, we'll see we can neglect the angle theta. In other words, it doesn't so much depend. If you start out here, what happens? it speeds up, it has enough time to speed up, so it goes pretty fast. If it starts here, it doesn't have much time, so it doesn't go very quickly. So it covers more distance here, but faster, and less distance, but slower. So it turns out that the amount of time is compensated for. And it turns out that it depends only basically for small angles on G and L. Now, here's a little trick called dimensional analysis, and this is something you can find very useful in work sometimes, that what kind of formula would we come up with if we said that T, the amount of time, should depend on G and L? How would you create a formula that would give you the right answer from T equals something to do with G and L? Should the amount of time be more or less the bigger G is? What would you say? It should be less. Why? The faster it's going, the less time it takes. If G is really big and it's going to pull it down, right? And L, if L gets bigger, does T get bigger or smaller?
Bigger.
It takes more time to longer L. So if T is related to this, it should have what on top and what on the bottom?
L.
L on top and G on the bottom. Now let's look at the units. What are the units of G? Meters per second squared. What are the units of L? Meters. So what does this come out to be? What units? Seconds squared. What do we want?
Seconds.
Seconds. So what would you do to this equation to get seconds squared?
Square.
And that's the right formula. Now isn't that amazing? All right, we found that obviously if you have an extremely long string that's miles long, right, even though it makes a small angle at the bottom, if this is 10 miles, then this is 1 mile, right? If it's at a small angle, it means it's at a small height. So gravity is going to act on it, not, it's not like falling from a high distance. It's just going to move through a great distance here, most of it which is, at a very low angle. But it's going to move through a great distance, it's going to take a long time. Clearly that'll take a lot longer than a string moving through the same angle, but much, much shorter. So the length of the string will make a difference. Obviously it should be on the top because it's proportional to the time. Mass, we said, well, maybe it should make a difference, maybe it shouldn't, but then we remembered that all masses fall with the same acceleration. So it shouldn't matter. The reason that the pendulum is falling is because of the pull of gravity, but it doesn't matter which mass is going to pull it down with the same acceleration. But it's the acceleration does matter. Obviously the greater gravity, the faster it's going to fall. So G, little g, does play a role, but M doesn't. All right, and obviously it's inverse because the greater the gravity, the faster it'll be moving. All right, so we derived this, and then we found that L over G didn't give right units, it gave seconds squared. So we said, let's just take the square root and see what we get. So we took the square root of L over G, and we found this equation. Okay, equation 3.2, T equals 2 pi L over G. Of course, we didn't do the 2 pi, that's just a numerical constant. Okay, where does the angle come in? It doesn't. But look at equation 3.1. That's actually the more correct equation. 3.1 has this with a whole factor over here, 1 plus all kinds of things depending on theta. For small angles, all those things are very close to 0. Okay, for small angles, all of that is close to 0. Sine theta over 2 is not that large, and if you square it, it becomes even less, and then divided by 4, it's even less. So most of those terms can be neglected for small angles. For larger angles, where sine theta is closer to 1, you can't ignore those. Hooke's law is simply that equation that we've seen before, F equals minus kx, where the force of a spring is proportional to the amount of distance that you stretch the spring or compress the spring. And obviously, if you compress the spring this way, the force of the spring will be back that way, so it's negative. If you stretch the spring this way, the force of the spring will be back the other way. So it's always negative to the displacement amount. So this is the amount that you displaced it, the force will be in the opposite direction to the displacement. Let's not line this up. That when we change the stiffness, it'll hang differently. Right? The mass will hang higher or lower. Okay? Now, what are the units of this K? We know the units of M. We know the units of G, is acceleration. X is just distance. What is this? Okay, the units of this has to be force per meter. Okay? Force is the same thing as this is. So it's the units of this over X. Right? The units of K are obviously mg over X, same units as mg over X. So the units of K are kilograms. G is meters per second squared divided by the units of X, which is meters. So the meters cancel out, and what do you get? Kilograms per second squared. All right, so the units of K are kilograms per second squared. You have F is equal to minus K delta X. That displacement with delta X is X minus the X0, depending on where you started from. Skip the part on the right-hand side about Young's modulus. You have F is equal to mg. In other words, you have a spring with a weight on it. All right, you have mg going down. It stretches the spring. You're not talking about when it's oscillating up and down. You let it go down and you held it so that it's not moving, and you let it go when it wasn't balanced, equilibrium. So there's obviously a balancing force up this way because it's not accelerating. That force is equal to minus Kx. This product has to equal mg. If this is fixed, if K is bigger, the X displacement will be smaller. If K is smaller, the X displacement will have to be bigger. Right? But we're talking about in terms of, you take the mass, now it's, let's say, stretched down to where it is. And you're all right about saying that the amount that it's stretched is determined by the stiffness of the spring, okay, in terms of this product. Okay, so if you measure the amount of the spring stretched, you know how much X is. If you know the mass, then you know mg. If mg equals Kx, and you know K, then you can determine X. Or if you know X, you can determine K. Or if you know K and X, you can find M. Or if you know Kx and M, you can find G. Whatever, Kx equals mg. Okay. If you add more masses, obviously just the total mass. Simple harmonic motion, section B. If you do let it go when it's stretched or compressed, it will obviously, as we mentioned many times before, go up and down, up and down, up and down. Without air resistance, it'll continue going up and down. Because of air resistance and the friction within the spring itself, it'll slow down eventually. Let's say you take a spring at rest, not stretched, add a mass, and it stretches this much, and we call that X, or delta X. Now we're talking about, we're pulling it down an extra amount to make it oscillate. Here it's not oscillating, just standing still. So if this is X, then really what we're talking about is pushing it down a certain amount Y, stretching it, and then letting it oscillate up and down. Okay, so this delta X is just to get equilibrium. We let it go just standing there, because Fx equals mg at this point. And this is an extra amount Y that we stretched it to make it go up and down. Now, let's say we wanted to get an equation for the period, okay? As opposed to a pendulum, now we're doing the period. This was for a pendulum. Now we're doing it for a spring. All right? What might we think that we should have there? Here we had L over G. What things didn't happen in here? We didn't have M in here. We didn't have theta in here. There were a lot of things that might have been in here that weren't in here. What, should this be exactly the same formula? Yes, no? If it would be, what would L be? Would be X would be how much you stretch the string. Let's say we did it this way, okay? We're already alerted to the possibility that we might need a square root or something like that. Let's say that we're assuming that we're going to have a square root of something, okay? And which things can we put together in such a way that it'll give? Okay, So is that reasonable, not reasonable, physically?
Well, I mean, if you think about it in terms of force, the more mass you have, the more, I don't know why it would be different from the pendulum, but the more mass, the more it's going to stretch.
Okay. So here we have a good consideration. The more mass there is, obviously, the more it's going to stretch the spring. As opposed to the pendulum, it was just like falling down in gravity, and gravity doesn't distinguish between different masses, right, in terms of the acceleration. The acceleration of gravity is the same for all masses, so we make a difference. So there's a possible reason why we should have m in here somewhere. Okay, as opposed to the case of the pendulum. What about x? Okay, what about x?
The mass determines how far it goes, right?
Right, the mass will determine how far it goes. So we have F is equal to kx, and that will have to be equal to mg. Okay, I'm not going to worry about the signs right now. Basically, this amount is determined by this. Okay, so there's some relationship between the two. Okay, but still, we might think maybe we do need it, maybe we don't. All right. What else might be in here?
Well, okay, you have
Okay, should that be in there or should that be in there? The K is one of the factors in here, so it certainly could play a role. Let's say, why would it play a role?
well, the T we're trying to get the period
Of, let's say, one complete cycle.
I guess the K would just make it a shorter displacement, but it might not necessarily.
Okay, let's say given everything else the same, if we have everything the same except we just change the K. So what'll happen? The mass. Well, if let's say the stretching amount is the same and the mass is the same, well, okay, we're pulling it and letting it go and going up and down.
Yeah.
Okay, so we pull it the same amount and it's the same mass and whatever, just that the K is different. What'll happen with the higher K or lower K?
But how, if the string is pulled, right?
Yeah.
And there's a mass pulling it down, right? No. The looser the string, right, the mass will pull down further, right?
Right.
So if K is greater, then the distance is going to be shorter.
Right. Right, that's true. That's in terms of this. If K is bigger. But now after it's in equilibrium, we pull it down a little more and then let it go. It's going up and down. Okay? How will it be different given the same mass and the same whatever? Just let's say the stiffness of the spring is true. If it was stiffer, it would be held up more. But if we displace, let's say, 2 centimeters, and the only thing we change is the stiffness, it's true that when we change the stiffness, it'll hang differently. Right? The mass will hang higher or lower. But in terms of the oscillation up and down in the period, okay, what does the stiffness do? So it'll pull it back faster. But then when it compresses, it'll press it down faster. Okay? So it's very possible that it'll change this. Right? So K might also be in there. Okay. Now the question comes about X and G. All right? Now, all of these things are really related. K, X, M, and G. All right? So it certainly seems possible you don't need all of them. You don't need K, X, M, and G all in that equation. Right? Because they're related to each other. One determines the other. You certainly don't need all 4 in there. All right? Now, which thing would you suppose? Which thing has to be in there? What would you say if I said there were only 2 quantities? Which one quantity? You know, like Certainly should make a difference.
Gravity.
Gravity, okay. Also? X, okay, anybody else? K. So basically we're getting back all to the same ones. They all seem indispensable. Okay? But we know they're all related. So now, what happens?
Gravity's constant,
Right, but in different planets or further away from the planet or something like that. In other words, where are we changing G? Because it depends on that. It's true that all our experiments will take place basically with the same G, but it does depend on that. If you might say, for example, that maybe the stiffness doesn't matter, because if it's more stiff, then it'll hang closer up, and then if you pull it, it'll go faster, and somehow one cancels the other. Did that happen?
Yeah. The same, if it's force, right? And you let it go, it'll go right up, but the same force is gonna push it back down. So
Right.
it's like one cancels the other, so not really.
So you have to think into that. Does one cancel the other, right? Does it? And let's say the mass. I mean, in the same way that in the pendulum maybe it canceled out, maybe the mass canceled out, because although the mass hangs it lower, it maybe makes it oscillate faster or something. In other words, you have to think about it. It's not so trivial. You'll find that it doesn't depend on how much you're pulling it down. In fact, they do cancel out, the two effects. The more you pull it down, the stronger the spring force pushing it up. So it has to cover more distance, but it does so faster, and they exactly cancel out, which is very nice. All right, so the units of K are kilograms per second squared. All right, we know this is kilograms, and this is meters per second squared, and this is meters. Let's say we're going to have square root of something. If we have mass in here, is it going to be on top or on the bottom? Top? So we have kilograms over here for mass. If we have G, where would it be? The more gravity, the faster or the slower it'll happen?
The more K,
The more G. If G is bigger, T will be bigger or smaller? So it'll be inverse, okay? So it'll be at the bottom, so you can have meters per second squared here from gravity. If we had X, where would it be?
But if the gravity were more, it would accelerate faster. So the period would be shorter.
Yeah. Right, it's going faster, so the period is, the amount of time that it takes to complete a cycle is less. All right. If we had K in there, where should it be? Okay, why in the bottom?
because the unit is kilograms.
Well, no, but okay, that's afterwards. I'm just saying in terms of logic, where should it be?
Higher K, we need more time. Because
Higher-
The more K, we have more frequency, which is shorter time. So inversely.
So inversely related, so it'll be on the bottom. Okay, so if there's a K, which is kilogram per second squared, it would be here. If there's an X, where would it be? Okay, the more distance you pull it down, what happens? The more distance you pull it down, the longer it has to travel, but also the greater the force. Right? The more you stretch it, the more force there is in the spring, and also the faster it'll go. It has to cover a bigger distance, but with more force. Okay? So the X might, there might be interesting thing of the X kind of canceling out. Right? So we're alerted to the fact that the X might even cancel out. Okay, the displacement. That's actually a Y. So let's say, really, we're going to use maybe the letter Y here rather than X. Okay, it's not that delta X amount exactly this, but it's an extra amount stretched. Okay, but in any case, we're alerted to we don't know to put it on the top or the bottom because it both makes the period faster and slower. Because the more you stretch it, the more distance it has to cover, but the more you stretch it, the faster it's going to move because there's more force pulling it up. So it's not clear. So let's say of these three, what could we arrange that would make sense, that would make the units fit? one? Which two out of these three fit? Okay, if we had just these two, what would be the units? It would be meters, kilograms per second to the fourth. 1 over that, so it would be second to the fourth square root of second squared over square root of meter kilograms. Kind of weird. We want to get time, all right? Which of these quantities can we put together to get time, for example? If we had just these two, what would we have? Square root of second square on the top, so it would be seconds times kilograms over meter square root. What about this one and this one? What was this one? This was mass, and this was K. Works. Kilograms cancels kilograms, second square comes on top, square root of that is seconds. M over K. If you did it upside down, it wouldn't make sense logically, because if K is in there, it should certainly be on the top. If M is there, it should be on the bottom, and also be 1 over second. But if you're doing frequency, which is how many times per second it goes, which is the inverse of t, then it will be upside down. But if we're doing the amount of time, then it works both logically, that k should be there and m should be there. If k is there, it's on the top, and if m is there, it's on the bottom. And also it works units-wise. It gives us the right units of seconds. And in fact, that's the right equation. Again, this is called heuristic. This is just kind of using our intuition and so on. This is not a rigorous way. You can't derive this rigorously. When you do, you find this is the right equation. But it's interesting to see how you can get to this using logic. Now, this is obviously not the way you derive the equation, right? You can derive it rigorously, or you can, in a laboratory, you can prove that, in fact, this is correct. All right? It'll be 1 over t. It'll be 1 over seconds. Y is the height displacement away from where it started, is equal to A. A is the maximum amplitude. Cosine 2 pi t over big T. Big T is the total period. T is the amount of time that has passed, like what fraction of a whole period. And we'll get to this whole thing later, but that's the more exact description of the oscillation. If you wanted to graph how high it is at any point, given the amount of time that has passed as a fraction of the total period of. You'll put t in, the amount of time divided by the total, take a cosine of that, multiply by the total amplitude, and that will tell you how high it is within that total amplitude. Okay.